we can ask, and I mean, I can just press one button to stop. So anyway, it's being live streamed. Okay, fine.
Where is Ilya? He's in Brazil. He attends. Okay.
So guys, I partially decoupled from you for some 5 minutes. I mean, I have to give a call. I'm here, so when Ilya will join, I will make him co-host. Just will be mute a little bit.
Oh, okay. See you soon. I'm also going to do something.
Okay.
I will make coffee meanwhile.
Алексей, здравствуйте. Здравствуй, Hero.
Да, здравствуйте.
Hi, Irina.
Hi.
I'm just trying to call someone, so I'm kind of mute, but then I will come back.
Okay, okay.
Hello, how are you?
Relatively fine. Yes.
Okay.
In fact, I'm participating in some conference in St. Petersburg, but in Zoom. Here, Ilya also supposed to give a talk, and maybe he's supposed to give a talk just today. Let me check
Okay.
If he can have some coincidence. Let me just check. What is this program?
What is the conference?
The conference is in St. Petersburg is dedicated to couple of physicists. One is Vasilyev. I don't know if you know his book. A book about path integral approach to quantum field theory and statistical physics, and another one also to a person, he passed away, Lichovsky. He is an expert in representation theory and application to physics. Let me check. No, I don't see. Kovalenko, Bazov, Mondrov. Not today. Fortunately, not today. No. I saw his name and I saw that he will give a talk in afternoon session. Yes. He will give a talk tomorrow. Effective quantum gravity, cosmological constant, and standard model of particle physics. Exactly
the same
talk.
Same talk.
But the same talk, but fortunately, in our seminar, he will have 1 hour, but here he has only 45 minutes. So
Ilya is here.
We have 1 hour and bit relaxed as well. So
okay.
Sorry.
Hello, Ilya.
hello, Ilya.
Hello.
Hi. How are you?
Nice.
Hello, Ilya. Yes.
Hi.
Hi.
Ilya.
Are you in the office at university?
Yeah, of course. The background tells that. I believe it's off.
Yeah, it's my office, exactly.
Okay.
Hello, Ilya. How are you?
Hi. Hi.
So, let me
You
make
see
you.
behind me on this side, on the top, is the poster of our conference of 2003.
2003. Okay.
Yeah, it was only once I did conference of this level here with, there were Jakiv, Desert, and many other people. So, but then we stopped doing this because it took too much time. So let me try to find my talk somewhere here. It should be. I just gave lectures on statistical mechanics. So
Are
if
you
I
in St. Petersburg now or no? Where are you now, geographically?
in
Physically.
Juiz de Fora in Brazil,
Ah, you're in Brazil, because I saw you talk tomorrow, will be tomorrow in St. Petersburg, correct?
yeah, about the same subject. Actually,
Yes, yes,
I
yes,
would
exactly.
probably start to change the subject. I could tell something else,
Okay,
actually. If you want,
but-
I change now.
No. I'm afraid that maybe these two talk coincide, because I remember that you were supposed to speak afternoon session in St. Petersburg. So I just checked to be absolutely sure that you are not supposed to be simultaneously at two conferences.
No, I will speak online, because I cannot go, because I just came back from Italy.
Mhm.
And so from many points of view, it's impossible to go. Maybe I go to Tomsk in January if I can, but not now.
Oh, yes, it is difficult. It is really difficult now, yes.
Yeah, so let me go this, share. Do you have the slide?
Yes, very
Yes.
good.
Ah,
Maybe you can try to full screen, but this is up to
Sure.
you.
yeah.
Because sometimes full screen is less bigger, is smaller, in fact. Ah, great. It's very good, very good.
No, it's basic PDF, so it's not supposed to give problems. Also, I gave this in many places. Manuel has already listened to this like 10 times.
Oh, very good, yes.
But he said that the best one was in Huelva, which was 15 minutes.
Mhm.
Because if I make it more than 15 minutes, then people start to ask more questions.
By the way, is it okay if they stop you, interrupt somewhere in the middle of the talk, asking?
In principle, yes. Why not?
Okay.
If I
Okay.
don't like to answer, I will tell this honestly. So please don't ask me.
Okay. Okay. And is it okay that we are live streaming and then recording it on YouTube?
Sure.
Okay.
Sure. Why not?
No, but we have to ask you, because sometimes people don't want to be recorded, in fact.
No, sure. Professor Efeva, what is your second name? I mean, Irina, I forgot.
Irina Yaroslavna.
Oh, Irina Yaroslavna, and you are not in St. Petersburg.
No, unfortunately, I was supposed to go there, but then I'm afraid that maybe something happens, and I decided to stay at home, yes.
Buchbinder is there.
Yes, I know. He asked me some questions during my talk. Yes, so I asked, who asked me the questions? I cannot recognize the voice. Maybe he was a little bit disappointed, but he said, I'm Buchbinder. Yes, now I know, of course, him personally, but Zoom changed the voice, maybe, I would say.
I could not yesterday listen any talk because, first of all, there is a huge time difference. It's 6 hours. And second, I have grandson. And yesterday he visited our home for the first time.
Ah, I see.
And tomorrow he will be 6 months old.
6 months. Okay. What is his name?
Congratulations.
Yeah, sure. Oh, hi.
Hi, Richard.
Richard. Name is Levi. Don't ask me why my son gave this name, because he did not consult us, actually. So. Just a second.
What's the weather in Moscow now?
Today I stay at home about 9 degrees, so it's not too warm. Yes.
Well, here it is
Yes.
14, 13,
Mhm,
14.
In Brazil, it is one of the first hot days of the season.
Yeah,
So
yeah,
now we
yeah.
will have like
Spring.
half a year of that hot. Жизнь до фора is not really hot, but now it is almost on maximum.
Is it summer there? No. in
The
Brazil?
summer is starting, yeah.
Okay, okay.
Summer will be until the end of April, basically.
I remember when I went to
didn't know it.
Brazil, in that time in Moscow was about -35. It was in January.
Yeah,
And in Brazil, it was plus 35. So 70 degree
degrees.
of difference. It was
Yeah.
too much.
Yeah. When Valery Frolov visited us for the first time, he called me home that he went from Edmonton.
Mm.
And he asked my wife, what is the weather? What I should take about clothes? And Lena said, you need something warm because it's actually not hot at all. He said, Lena, what do you mean warm? Because it's like here is -30. She said, no, here is +20. Not warm, it's +20.
Plus 20. Okay.
I remember once in Rio, it was the temperature fell below 20. I think it was between 18 and 17. And the ladies wore really fur coats.
Mhm.
Yeah. So for them, 18 is extremely cold.
Mhm.
Yeah, but there are in Rio, Farina told me that Farina or somebody else, maybe Nelson, told me that there are every winter there is special night when the temperature drops to 12.
Yeah, because there is it might happen that the air from Antarctic comes. I witnessed it.
I think it's just accidental. And ladies who have this, expensive overcoats from real skins and things like fur, and so it's their day. So this night they make a walk on the street because other days it's not a good idea.
Yeah. Is everybody there? No, 20 people.
I guess maybe a little bit Italian tradition, because once I was sometime in Roma, it was in the night, it was 15 or 12 degree plus, but many women have, no, not many, some of them have the overcoat from Ming. This is very luxurious. But
sure.
maybe we have
in Italy, if you go to opera, then old ladies all use this Norca overcoat. I don't know how to say it in English.
Mink.
Yeah, and those who don't have feel bad. It's obvious. Luca will confirm. So should we start?
1 minute. Well, usually we wait a couple more minutes because people arrive at the last moment.
No, sure. No problem.
I think we just wait a few minutes. In fact, many people from St. Petersburg usually participate in this conference. I'm not sure about them because this section is not yet finished. I check, they will finish in a few minutes. I don't know, but maybe people are tired today.
Richard, and you come in April or not?
I hope so. Yes, I come. I hope that I'll come. I'll be able to
Good.
come.
Great.
It's in Ubu.
We don't know because it seems we will have financial problems this time because we were refused in all places for a while. So Julio is thinking to move it to Pedro Azul.
Pedro Azul. I see. But there's no
Which is not
seashore.
standard.
It's not on the seaside.
No, it's in the mountain.
Yeah. It's close to.
But my opinion was that it's a good idea because he had some good conditions in this place.
Yeah.
Actually, in April, maybe on the seaside, you also can find good conditions because it's not a high season at all in April.
Yeah.
So it depends on that.
Yeah. Okay.
Okay, maybe we can start. Good evening or good morning, everybody. Today we have a pleasure to listen the talk by Professor Ilya Shapiro. He will tell us about effective quantum gravity, cosmological constant, and standard model of particle physics. 1 hour, please, Ilya.
Okay, let me first of all thank Irina, Alexei, Sravan, and Luca for invitation. It's a pleasure for me to join this system of online seminars. Some of them I could listen and they were very interesting. So I will give the same talk as I started to give this year from February. So it's about several subjects which we tried to put together with Brenna Giccini and Tiberio Paolo Nieto. And so I will start describing the cosmological constant problem in a standard setting, then discuss a little bit how we can construct a renormalization group for the cosmological constant, and then concentrate on the quantum gravity aspects of renormalization group running of the cosmological constant. And here we meet serious difficulties with the gauge fixing and parameterization dependence in quantum gravity because we have to do it in effective framework. And in this framework, this is a serious issue. And then finally, we will see that if we use this Wilkowski-DeWitt unique effective action, and we come to strange results which restrict the models of particle physics beyond the standard model. So I will start. So first of all, what is the cosmological constant problem? We know that cosmological constant is a constant which you can put to the covariant Lagrangian of gravity together with the Einstein term, Einstein-Hilbert term. And you can measure it in cosmology by analyzing the accelerated expansion of the universe, for instance. And then, like many talks about the so-called dark energy, which drives the accelerated expansion of the universe, mention that cosmological constant term is a big problem because it can be calculated in quantum field theory from the first principles. And then it has a value which is 120 orders of magnitude greater than observable value. And this means that we have a big scientific problem. And this is not true. In reality, cosmological constant is an arbitrary parameter in quantum field theory, in quantum gravity, in any theory we know. And so in quantum field theory, in principle, we cannot calculate any arbitrary parameter from the first principle. So what they described story about 120 orders of magnitude difference is basically doesn't have big sense. So in cosmological constant is not an exception since it is an independent parameter, so we can calculate contributions to it from the loops of matter fields or loops of quantum gravity, and typically this quantity is divergent. So in quantum field theory, typically all quantities are divergent. So it does not mean that we have to scare, because many years ago people developed the scheme of renormalization. So we have to subtract the infinite value for any parameter, including massive parameters such as cosmological constant, and then impose randomization condition, and you get your finite quantity, which you have. So for independent parameters, typically to fix the value of the any parameter, you need a measurement. In this case, measurement is a cosmological comes from cosmological observations of very different kind. So I like to cite this statement of Pauli that not all quantities which are calculated to be infinite are in fact equal to 0. So this 120 orders of magnitude difference correspond to the following scheme of calculation. Rho lambda is a quantity of dimension mass 4. So if you use cutoff regularization then and impose that cutoff must be of the Planck order of magnitude, then you get huge value. But this means why we should consider cutoff of Planck order of magnitude if the measurement is the cosmic scale, well, the typical length parameter is Hubble parameter. It's not obvious. Then if we decide that all physics must be calculated from the first principles and start to impose this scheme with the Planck cutoff to all physics, then we should have problem with electron mass, tau mass, and so on and so forth, because everything is proportional to the square of the Higgs mass, and the Higgs mass gives you a square of the cutoff parameter. In reality, of course, we don't have anything of that because we have to make a normalization. Actually, it's not possible. It's possible to construct a very artificial scheme when you have 120 orders of magnitude. I'm proud to say that in this textbook on quantum gravity, which we published last year, in the last chapter, you can find one, but it's very exotic. It's very exotic, has nothing to do with the real physics, I would say. So now let's go to measurement. The measurement means, in our case, a full set of available observational data like supernova, cosmic microwave background, large-scale structure, baryon acoustic oscillations, and so on. And these measurements typically are done in the scale of the universe or at the scale of cosmic perturbations, which is not exactly the same thing. But anyway, the all set of these data converge to the quantity like Rho lambda today observable is like 70% more or less of critical density today. So if we look to the situation from this point of view, there is no problem with the cosmological constant term at all, because we observe something, some value of independent parameter lambda, and this is fine. We cannot complain about that. Actually, cosmologists, they typically take this position. So they do not consider cosmology as the department of quantum field theory. So for them, Rho lambda is something, some measurable quantity, and they basically are worrying about two things: the value of this quantity and whether this quantity can change during the evolution of the universe. However, from the point of view of quantum field theory, we really have cosmological constant problem, and it comes from the following situations: that there are huge, really big contributions to observable cosmological constant, and they come from different, completely unrelated sources. For example, you need independent parameter, cosmological constant, to have consistent quantum field theory in curved space, at least if you have massive fields, and we have massive fields. Second, there is a so-called induced cosmological constant contribution, which means that you have some phase transitions in the universe. And as far as we live in the vacuum, which is the result of, let's say, spontaneous symmetry breaking, then we have, once again, huge contribution to the cosmological constant. And on top of these two big contributions, it's possible to have small variations of this cosmological constant because of quantum effects of some kind of running, not necessarily minimal subtraction running, like in Young-Mills or QED, but maybe a different kind of running. But in principle, it cannot be completely ruled out. So let me start describing these contributions because it's important for us today. First, this year we can celebrate 60 years of this famous paper, very important paper by Uytiyama and David, who basically established the structure of randomization in curved space. space-time, and we know that divergences starting from this moment, we know that divergences are first of all covariant if we use covariant regularization, and second, they are local quantities. So it means that if we want to quantize matter fields on curved background, then our vacuum action should include those terms which can appear as divergences. So in particular, it's Einstein-Hilbert term with cosmological constant and 4 structures with 4 derivatives each. So if we do not put lambda, which I call lambda vacuum, in our original theory, then we will have trouble because you will need to this quantity to make renormalization. If we put it 0 from the very beginning, then we cannot use, let's say, standard procedure of renormalization for this parameter, and this is not good because, in principle, it does not. It's not impossible, I would say, but it makes our theoretical life inconvenient, at least. So the next question is, what is the natural quantity of this independent parameter, which is lambda vacuum or rho lambda vacuum, better say? So in order to answer this question, we have to rely on renormalization group, as people do in many situations. So if we go to the very early universe, then we can assume that the typical energies were very, very high. And then we can expect that these parameters were running according to the minimal subtraction scheme of renormalization. In the later universe, we can assume some kind of decoupling, like in Appelquist-Carasoni theory. I will discuss this a little bit in what follows. But in the very early universe, there should be just a naive minimal subtraction running. And this gives us the situation when lambda vacuum runs according to the force powers of the fermions and scalars. So in our case, this means that this quantity is typically like 10 in 8th power GV4. The same running for the inverse Newton constant is not so important because if we restrict our attention to the minimal standard model, then we have here square of the fermion square of the scalars, and this is anyway much, much less than the square of the Planck mass, which is here. So the running of inverse G is weak, but the running of rho lambda can be huge according to these formulas. So you have to impose that the parameter itself must be of the same order of magnitude, otherwise it changes too much in this scale. Let me say that this running for the cosmological constant is a non-trivial issue. Okay, I will not discuss this in this talk, but in principle, this was discussed in the literature, and I can explain if necessary. But it's completely non-trivial point because, let's say, in the momentum subtraction scheme in the flat background, you cannot see it. And so, what means the running of the cosmological constant in curved space is an open question. So, the second contribution to the cosmological constant density is this. So we, according to the minimal standard model, we live in the minimum of this vacuum, and in the minimum of the vacuum, you have this contribution to the cosmological constant. So we shift the value of our zero as in this plot, and what we observe as a cosmological constant is exactly the size of this gap between the axis, horizontal axis, and the minimum of the curve. So we see that here again we have the same contribution in the order of magnitude. If we restrict our attention to the minimal standard model, then this induced quantity is like 10⁸ GV4. So of course, what Zeldovich found in '67 was different, but it's in both cases it's induced cosmological constant. Once again, there is big literature about this, but I prefer not to discuss it because I want to come to my subject. So what is observable cosmological constant? The observed value is this quantity, is a sum of vacuum plus induced. There may be other contributions, of course, from chiral phase transition and so on, but in principle, the main two contributions are this. So now what means the renormalization condition? Out of these three quantities, rho lambda observable is what you measure. Rho lambda induced is what you can, in principle, calculate from the spontaneous symmetry breaking in the standard model. So independent parameter is rho lambda vacuum, and you define it as a difference, okay? And you define it at some scale mu cosmic. And this is the main formula, basically. This relation is the main formula because it shows how we define the vacuum cosmological constant. It's rho lambda observable minus rho lambda induced. The curious point is that these two quantities, rho lambda vacuum and rho lambda induced, are of the same order of magnitude, but they are huge compared to the observable quantity. Observable quantity is like 10 minus 47 GeV4. And so the observable, the sum is 55, 56 orders of magnitude smaller than these two sums. So this means that these two terms should cancel, okay? But we cannot explain why they cancel. Okay, we can say that they cancel because we can live in this universe and so on and so forth. But we cannot explain why they cancel, and this is a cosmological constant problem. And one can say that this is too much because it means that we have defined the quantities of rho lambda vacuum and rho lambda induced, at least the magnitudes, as the energy scale of particle physics, which is like 100 GeV. And then we won't go to the energy of the Hubble scale, which is like 40 and something orders of magnitude less, and make another measurement and connect two things. They do not connect at all, and then we complain. But this means that we want somehow to have a unique theory of everything. And physics never achieved unique theory of everything. Maybe physics is not done for achieving a unique theory of everything. So when we want to solve cosmological constant problem from some first principles, it means that maybe we won't go beyond the framework of physics in general. So it's a kind of hierarchy problem, and it's very difficult hierarchy problem, of course. So I will give some more comments about this, but let me now say that in what follows in this talk, we just accept that this fine-tuning somehow takes place. So rho lambda vacuum is defined with 55 orders of magnitude precision. And regardless, we cannot explain this, we just accept that this happens. So there are some extra arguments. For example, if we try to solve the cosmological constant problem from the first principles, the first step would be to derive the rho lambda induced with a given precision, and it requires explaining the mass spectrum of the standard model with the high precision from the first principles, and then you have to take into account higher loop corrections and lower loop corrections. One my colleague calculated that you have to make it up to 21 loop precision, and after that you have to try to explain the cosmological constant problem. And this is not easy to imagine that this could be happen someday, let's say. Now, things are actually worse than I described it because there are so-called anthropic arguments. And Weinberg wrote a very interesting paper in '87 when he calculated what should be the value of the observable cosmological constant in the universe which admits our own life. Then people tried to improve this estimate and made some heavy assumptions about this. I will not discuss this, but the first paper of Weinberg was astonishing because he calculated the observable cosmological constant cannot be negative, it cannot be zero, and it must be positive, and the magnitude can be at most 100 times greater than what we see. So what it means? It means that somebody defined in the beginning of the universe rho lambda vacuum with a precision of 55, 56 orders of magnitude. If he or as this creator of the universe makes a mistake of in the last 2-3 digits, we cannot exist. Okay, and the worst point is that at the early universe, when this was done, it was not fine-tuning to zero or almost zero. No, because rho lambda induced, we can suppose that there was a symmetry restoration in the early universe due to high temperature. So universe was prepared beforehand, before phase transitions, expansion, and everything, such that after all this, we can live in this universe, which is makes everything completely non-trivial, of course. So we will not discuss this solution of this cosmological constant problem in this talk, and I will go to smaller problems, And what I will do is the following. I will discuss in some particular physical theory what happens if rho lambda vacuum changes a little bit. Because if rho lambda vacuum changes a little bit, during the cosmological evolution, then this very, very precise 55 orders of magnitude fine-tuning may be broken. And if it is broken, we have a problem. So in this way, we can get restrictions either of underlying physics, which explains us, for example, lambda induced because they must be equal, or the way we estimate this change of lambda value. So something, if we are lucky, we have to sacrifice something. If not, everything will go smooth. So let's see what happens. So first of all, what means the running? So in QED, the standard arguments is that you have RZ. So you have original action with F mu square, classical, and then you calculate one loop polarization operator contribution, and you have this logarithmic form factor. Actually, this is approximate formula. The correct formula is much more complicated. So at low energies, this logarithm becomes a number. So there is no running at all. But at high energies, in the ultraviolet, in Euclidean momentum, then you have this running of electric charge. This means that instead of working directly with a non-local logarithmic effective action, which is very difficult to work with because you need to impose boundary conditions for the non-local terms and so on. So you can perfectly well work with the running charge, which is easy. And then if you go to atomic physics laboratory, you have one charge. If you go to lab, you have another charge, and you work basically always with the classical theory, which is good. Now, the real formula for beta function is like that. Here A is this formula, and this you can see that in high energies you have normal, let's say, minimal subtraction beta function, and at low energies you have quadratic decoupling. This is called Appelquist and Carcassonne theorem. In semi-classical gravity, we calculated this with Eduard Gorbar from Kiev almost 20 years ago, and this was like recalculated by us and by many other people after. So including this formula is a result of one of these calculations. So qualitatively, it means that minimal subtraction beta function provides you a linear running on the plot of 1 over inverse square of the electric charge and this T, and the physical momentum subtraction beta function gives you this. In high energies, it's the same equivalent plot, and at low energies, it frees down. Now, this is very nice, and the idea is that we would be very happy to apply the same scheme to quantum gravity, because in quantum gravity, different from QED, effective action is more difficult to calculate, and actually it's not very well defined. So if we can evaluate somehow beta function and apply all this story to quantum gravity, would be great. Now, so as I said, the situation with the running of cosmological constant is non-trivial. You can see like this paper with, I think, most complete discussion was given by Joan Solan and me in 2009 in this paper in Physics Letters P. So the question is really open, at least in my opinion. So you cannot prove or disprove that this running may take place, at least in the semi-classical gravity. The same actually in quantum gravity. So this is not what we discussed today. Today we discuss how it works in quantum gravity, in real quantum gravity when we quantize matter. So first, a statement about quantum gravity is that if we start with covariant classical action, we can have a covariant quantum theory in all loops. The first proof was done by Stella in '77. The last proof was done by Professor Lavrov and me quite recently, and with Batarin-Vilkovsky formalism. And so you can prove that even if your starting theory is non-local, the divergences are local and satisfy the power counting arguments. So this is the first statement. So this noether identity holds in the quantum level, at least for the both for divergences in 4 dimensions and finite part. Second point is that if we want to use this quantum gravity for ionization group, the question is which model of quantum gravity we can choose. And the second question is whether we can be sure that our beta functions, which we obtain in this way, are unique. So first of all, let's pay attention to the Fadeev-Popov quantization of the theory, or the Witt-Fadeev-Popov quantization. So we have this gauge fixing term, and so we have Gauss term, And we see that in quantum gravity, even in Einstein gravity, we have two parameters of the gauge fixing, alpha and beta. And on top of that, we have a lot of parameters which characterize ambiguity with the background field method, with the choice of quantum metric. At one look, there are like 8 parameters, if I'm not wrong. So then we go to power counting and we see the following. This is very important for us today. This is the main formula of power counting. Omega is divergence of the diagram. If there are only logarithmic divergences, it's 0. D is the number of derivatives in the external lines of the diagram. Like in Einstein theory, it's 2 or 0. 0 means cosmological constant. RL is number of momenta in the denominator of propagator. V is number of vertices, and K nu means which type of vertices we have. Like Einstein gravity gives you K nu equal to 2. Einstein term gives you K nu equal to 0. For derivative theory, 4, and so on and so forth. And then there is also topological relation. If you combine these two formulas for Einstein gravity, we arrive at this relation. This is exactly the main relation of this talk, which is on the bottom. Why? Because it shows that in Einstein gravity, with the growing number of loops, L, you have more and more divergences, more and more derivatives, in the divergences of the logarithmically divergent diagrams. So without cosmological constant, you always have 4 derivatives at one loop, 6 derivatives at 2 loop, and so on and so forth. But if you have cosmological constant, then from the very beginning, then there are vertices from the cosmological constant which decrease the number of derivatives. Like at one loop, instead of 4 derivatives, you may perfectly well have 2 derivatives, or even 0 derivatives if you have 2 k lambda vertices, and so on and so forth. If you go to higher loops, then you just need to increase the number of vertices with the cosmological constant, and you have all types of counterterms, like cosmological constant counterterm and Einstein Hilbert term and 4 derivatives, and so on and so forth. So in Einstein gravity, according to this formula, at one loop without cosmological constant, so we see only 4 derivative terms. This was calculated first by Hoften, Veltman, Deser, and Ewenhuizen. And so at 2 loops, we have these structures. And this last is very important because it does not vanish on shell, which is important. So if we do not put cosmological constant, there is nothing interesting because our purpose is to have running of the cosmological constant, and it doesn't happen. There is nothing like that. But if we put cosmological constant from the very beginning, then at one loop, we have this divergence of the cosmological constant R type and this divergence of the cosmological constant type, and so on and so forth. So we have to start with the theory with the cosmological constant. Second, of course, we can take renormalizable or even super-renormalizable theory of quantum gravity with 4 derivatives, 6 derivatives, 8 derivatives, or infinite number of derivatives. However, what has to be taken into account is the following: that all these theories have typically gravity, which is a massless degree of freedom, and they have some set of massive degrees of freedom, and typical mass is of the Planck order of magnitude. So if we go to low energies, these massive loops or their contributions to the mixed loop loops are supposed to decouple. And this means that in the low energies here means exactly below the Planck scale, we go back to the quantum effects of Einstein gravity. So this was noticed by John Donoghue in this paper of 94, when he just made an observation that Einstein gravity, quantum gravity, is a universal theory of quantum gravity, is the infrared of quantum gravity, not only of classical. And from this perspective, we have to, if we want ionization group at low energies, and this is what we want running below Planck, not above Planck, we have to work with gravity only, and then we have to work with exactly with Einstein gravity. So the question is, how we can do the so-called effective quantum gravity, how we can do to the low energy quantum gravity and separate it from high energy quantum gravity. In principle, it's possible, but you have to remember that in this case, your propagators and vertices should be constructed on the basis of general relativity without 4 derivative terms. And this means you can have other terms of action, but they just serve to make renormalization. They are not serving as a basis for quantum theory. It's similar to vacuum gravitational action in the cosmology semi-classical approach. So let's do it. Let's try to do these things with the non-zero cosmological constant. And here we have the first result. The first result is that Christensen and Duff calculated these divergences, one loop divergences, and they got some result. But here we need some big problem, because we cannot use the result of Christensen and Duff because it's completely ambiguous, not completely, but very much ambiguous. So we know, starting from this paper by Kalash, Tarasov, and Tutin, that in principle, divergences in gravity depend on the gauge fixing. So it was noted by Fradkin and Tsetlin in 1982 that the combination, dimensionless combination of cosmological Newton constant has universal renormalization group equation. This is good, but this is not sufficient for our purposes because we need two. We need G and lambda. And there is also another detail which I will maybe comment after. Then there is another problem, that these divergences with cosmological constant or without cosmological constant, they depend on the gauge fixing and parametrization. It was originally noted in the paper by Arefьeva, Slavnov, and Fadeev, and then there were papers by Costa, Tanin, Voronov, Lavrov, Tutin, Kummer, and so on. So in principle, in quantum gravity, this formalism was applied by Fradkin and Tsetlin, and we, with Oskar Sheksenaev, my student at that time, explained this in such that it became understandable, let's say. And many people made also explicit calculations, like I would mention this paper by Kalmykov and our last paper on this subject when we worked with arbitrary parameterization, all in one loop. Very good. So what happens in this case is the following. You have one loop divergence in Einstein gravity with cosmological constant. The general form by power counting is like that. Then we know from these papers by Arefьeva, Slavnov, Fadeev, Lavrov, Voronov, Tutin, and so on, that the difference between the two effective actions calculated in different gauges are proportional to the classical equations of motion. So we just plug all this to this formula, and we see that these coefficients C1, C2, C3, 4, 5, 6 start to change because of this ambiguous coefficient B1, B2, B4, B5. By the end of the day, we have two invariants out of these 6 coefficients. We have two invariants. The coefficient of Gauss-Bonnet, this one, it's very important. This is not coefficient of Weil square, it's coefficient of Gauss-Bonnet, and the coefficient of this combination. This combination exactly gives you Fradkin and Tsetlin renormalization group, on-shell renormalization group equation. However, as I said, this is not what we want. So let us rely on the construction invented by Volkovitsky in 1984. First calculation was done by Barvinsky and Volkovitsky 1 year after, and then David generalized it such that it can be applied in principle to higher loops. So the idea is that this construction provides you a gauge fixing and parameterization independent effective action, even off-shell. And this is what we want. Of course, we have to be believers of this unique effective action. We cannot prove that this is better than any other effective action, let's say. But if you start to believe to this, then we have some possibilities. The first calculation of this unique effective action with cosmological constant was done by Taylor and Veneziano, and we recently recalculated using arbitrary parameterization and checked that everything fits in this and another paper parallel, which I cited at the beginning. So, what is the idea of Volkovitsky unique effective action? In principle, the idea is the following. If you take just a normal, not gauge field, simple scalar fields, let's say, then one loop effective action is a log determinant of the Hessian, of the second derivative of the action with respect to the fields. If we change the variables, then we see that we have, as we all know, we have here non-tensor law of transformation of second derivatives. And then on shell, when this derivative is zero, this derivative delta S or delta phi all vanish on shell, you have the same result, because if this is local transformation, then you have like at least divergences do not depend on this change of variables. However, off shell with delta S over delta phi taken into account non-zero, then you have a difference. And this is exactly the difference which we discussed in these formulas in gravity. So Volkovitsky and David approach makes the following. They replace normal variational derivatives to the covariant variational derivative. It means you introduce some metric in the space of the fields, then you calculate a connection in the space of the fields. With this connection, the second derivative transforms as a tensor, exactly like in normal tensor analysis. If we do this, then changes of variables are not harmful. And you can generalize it to the gauge dependence, which is much less simple, of course, but possible. And then by the end of the day, you have your construction gamma 1, which does not depend on anything. It does not depend on parameterization, does not depend on the gauge fixing. However, it depends on the fact that you believe to this scheme. Okay, let's believe to this scheme and see what happens. So the calculation of Taylor and Veneziano in ours gave this result. So this result is interesting because it does not at all depend on gauge fixing, does not depend on parameterization. So now we're in a good position because we have the counterterm which renormalized cosmological constant. We have this counterterm which renormalized the inverse Newton constant. And we can construct in a usual way with the minimal subtraction scheme this randomization group equations for the quantities of our interest. So you can solve these two equations and find these two solutions. These are interesting solutions for several reasons. For instance, you see, as I will show in the next transparencies, regardless, this formula is one loop, but at higher loops, we are not expecting to have any relevant corrections. So we can say that those are like exact beta functions, exact solutions also of randomization group. So if somebody goes to lattice, let's say, he verifies this running of these two quantities. If it has this standard with 4-5 pattern, better say 4-5 and 1-5, then we can say that Wilkowski-Dewitt effective action was proved by simulations. Okay, this is an interesting possibility, and I would be very happy to see the result. So anyway, we can go to the next level and see what happens in other sectors of the theory. First of all, but before, let me make some observation. You see, those are two one-loop formulas, the same as in the previous transparency. But they do not depend on gauge fixing, do not depend on parameterization, but they actually are not one loop. If we go to the next loop, then we see that the contributions are proportional to this quantity, lambda over m Planck square, according to the power counting, which I consider. And this is the same as rho lambda divided by Planck 4. Rho lambda here should be rho lambda, obviously, of vacuum, not of observable. But anyway, this quantity can be like 10, 12, at least orders of magnitude less than 1. So it means that second loop, third loop contributions, and so on are suppressed by huge coefficient like 10 minus 12 at least. Okay, this 10 minus 12 is when you have rho lambda vacuum very, very big. Not in the minimal standard model, which is much smaller. So it means that these two equations describe an exact running, not one loop running, at least for not unnaturally huge rho lambda vacuum. So now we can remember that the full action of gravity has this c square term, Gauss-Bonnet term, r square, cube of Weil, and so on. So, and all this gets renormalized, and we can construct these beta functions with this effective scheme for all these parameters easily. And all these beta functions will be exact. For example, this is the beta function for the square of the Weil term. Okay, this is with the contribution from photons and light fermions. This is the beta function for Gauss-Bonnet, also with contributions of photons and fermions. This is the contribution of Xi is like r square, and so on and so forth. So all these equations in this framework are exact, effectively, because two loop contributions are suppressed by huge coefficient. So we can do it even at start from two loop for this term, because one loop is 0, of course. But as Borov and Zeknoti calculated, we have this coefficient, and then we easily derive this beta function in this framework, our framework. And it is once again exact. It does not get any higher loop contributions. Okay, let's go back to our cosmological constant problem and see whether this discrepancy between vacuum and induced contributions really happens because of this ionization group equation calculated on the basis of Taylor and Venetian result. So the first observation is that the modulo of rho lambda is the modulo of rho lambda vacuum, because induced part does not contribute to quantum gravity. But numerically, it's equal to rho lambda induced, because they have to cancel. So if we take the strongest option, which means supersymmetric grand unification theory, then mx, the typical energy scale, is 1016 GeV. And then we can calculate that this quantity, gamma 0 over 4 pi square, is like 8 times mx squared over 4 over 0.4, which is about 10 minus 11. Then, since gamma 0 is small, 10 minus 11 is a pretty small quantity, then we see that we can linearize our running, and we have these two formulas. The first formula, as I explained before, is not very important because it's like 1 over 100 billion times correction to the value of Newton constant. But this formula is dangerous because, you see, rho lambda gains some contribution from quantum gravity, effective quantum gravity. And this contribution is proportional to rho lambda vacuum. So rho lambda vacuum is force power of mx. And gamma 0 here is also force power of mx. So this contribution is 8th power of mx. So it is very, very sensible to the mass scale. So the question is, what happens with the observed sum? Assuming that lambda induced is constant, we get this difference, that delta lambda observed is like that. So we have this formula. And if we put numbers, we see that this quantity is we can associate mu, the energy parameter, with h, which is a kind of a standard identification of scale. And then we see that this quantity is like 50 orders of magnitude greater than the admitted value for the cosmological constant, observed cosmological constant. What it means? It means, as I wrote here, if we believe in the Minkowski-de Witt effective action in quantum gravity, then supersymmetric grand unification theories are ruled out at this level. So we can say that Minkowski-de Witt effective action and effective approach to quantum gravity rule out supersymmetric gaps, which is strange because we actually did not work with the particle physics. The only impact from particle physics comes from lambda induced, right? But still, it is sufficient to make such a strong conclusion. Now, of course, we have to go to the lowest possible energy scale and look what happens in minimal standard model. In the minimal standard model, numbers are very much different. So we have Fermi scale over Planck, force power multiplied by force power in our rho lambda. And this gives you, instead of 10 minus 11, gives you 10 minus 65. When you multiply by rho lambda vacuum, which is still very big, we get minus 53. And this is nice, safe, 6 orders of magnitude less than observed value. It means that we cannot rule out minimal standard model. It's very nice because minimal standard model is possible to rule out, so it would rule out our considerations. Okay, and they cannot be ruled out in this level. But what we can see here is that this quantity is proportional to the 8th power of the mass scale. So if you, let's say, go to the energy, which is 10 times, which gives you basically the vacuum expectation value of the theory is 10 times more than in the minimal standard model, then you immediately get 100 here instead of minus 8. It means that in principle, you can survive probably in this universe because this difference occurs in the early universe, not now. Okay, but not even now we will try to feel the difference. So rho lambda changes too fast, maybe for observations. This is something would be interesting to analyze to see which kind of models of particle physics and of cosmology survive these restrictions. But this was not done for a while. So we can say at this level that in principle, if we really take seriously effective quantum gravity, and if we believe to Minkowski-Dewitt effective action, then in principle we can rule out some models of particle physics. And actually, what survives is the minimal standard model and the models which are not very much different to the minimal standard model, at least in the value of vacuum expectation value in the Higgs mechanism. Okay, so you may have in principle heavier particles, much heavier than VEF, but VEF by itself and induced value of the cosmological constant cannot be many orders of magnitude greater than in the minimal standard model. So here I have to finish. Let's go to conclusions. The first conclusion is that the great cosmological constant problem is very complicated, looks impossible to solve, because it is a hierarchy problem and it tries to put together some notions of particle physics and late cosmology. And these quantities naturally have completely different energy scales, belong to different physics, and they don't like simply to be put together. So if we accept the fine-tuning as a fact, this does not make our life completely free from the problem of the cosmological constant, because you still may have some violation of fine-tuning owing to the running of the observable cosmological constant. And now, if we believe to the effective quantum gravity, which is like, according to everything we know, should be a correct idea. So, and if we believe to Minkowski-Dewitt unique effective action, which is like one of the possibilities and cannot be ruled out, at least theoretically. So we arrive to some very well-defined running. And I would say also we have to believe that this running has something to do with reality. As I said, it's non-trivial, but this part I did not discuss. And so, but on the other hand, the equations which we get, at least formally, are exact in sense they don't get higher loop contributions, and they are completely universal. They don't depend on gauge fixing, parameterization, and so on. And in this way, we get some strange restrictions to the spectrum of the models beyond minimal standard model. Thank you.
Okay, thank you very much for your very clear presentation. Questions, please. Shravan, please ask your question. Yes.
Hello, Ilya. Thanks for the very nice talk. My so first question is about, well, you assume that it is lambda CDM, but now recent years H0 tension is challenging lambda CDM. H0 tension, the value of H0 from the local observations. So can you address this H0 tension from the effective quantum gravity approach? Is it at all possible?
This is interesting question, but because this is one of the possibilities for the running of the cosmological constant. And it would be certainly very interesting to see how these possibilities of running of the cosmological constant, this or semi-classical, may affect the H0 tensions. But in some, we actually work on this now. Okay, we have some papers about this. In 20 years ago, we had some publications with my colleague, and we have now recently with Giulio Fabris and Alan Taribio. And at the moment, one of them works on this, but since I'm not working on observational cosmology, so I cannot do it alone. So it goes as it goes. In principle, I would say that the answer is, in principle, yes, it can change things, because these tensions come from comparison of perturbations in different scales, and in case of supernovas, from analysis of expansion itself of the universe. So in principle, it can change things, yes. But to which extent, I cannot say.
Okay. Well, I have a follow-up question to your answer. So suppose if it is yes, and then how, let's say lambda is running and we can address possibly H0 tension. How to distinguish running of lambda with some quintessence model?
In principle, I would say that it's impossible, because it's my personal opinion, because quintessence and other models of this kind, they operate with potential which you can fine-tune. Okay, so you certainly can fine-tune. It was done when we published first papers on the running of the cosmological constant. The first thing people did, found the potential of scalar field, which gives you exactly the same expansion of the universe. Okay, and it was useful, but then you come to analyze the perturbations, and in principle, perturbations may you fit the expansion of the universe, A of t, but you don't fit perturbations. Okay, so in principle, there can be difference at the level of perturbations, of cosmic perturbations. However,
will be different.
However, if you make your model of quintessence or something equivalent more complicated, more sophisticated, like put second scalar and so on, probably you can fit everything.
Okay.
The question is how many parameters you will have and so on, things like that.
Right. Then
Okay,
it is a matter of taste, which one to be appreciated.
Yeah. So in principle, the statement like no one model of quintessence like field can give absolutely the same observational consequences, I would say that this is not true. You can. But whether the model with one parameter quintessence, for example, can reproduce the running, I would say no. Probably not at the level of perturbations. You cannot have it.
Okay. Okay. Well,
Okay,
as far as fine-tuning is concerned, you are also doing fine-tuning, right? You are canceling two effects from the induced and from the...
Yeah, but remember that quintessence does not alleviate the fine-tuning problem at all. It makes it worse.
Yes. Yes.
So 21 years ago, there was a conference in San Feliu in Catalonia, and at that time, quintessence was in the fashionable, and we were complaining on every talk about quintessence and saying, no, it does not solve the cosmological constant problem. And finally, I was banned and forbidden to speak. but I mean, 2 years after, the same people started to say the same thing as we were speaking, saying that quintessence does not solve the cosmological constant problem. So in principle, it is true, it does not solve. But on the other hand, you can have quintessence, why not? What is very difficult to have is zero cosmological constant. Because if you remember the beginning of my talk, you need a real cosmological constant to make a renormalization. So if you replace the cosmological constant by quintessence, you actually make things much, much worse. Much, much worse. Much, much, much worse. Why? Because it's hierarchy problem you have, okay? So you understand the origin of the problem. But if you remove cosmological constant and instead of it put quintessence, then instead of your hierarchy problem, you gain one more problem.
No, suppose you don't remove cosmological constant, but if you don't put it too small, but have the cosmological constant and have some quintessence field, then it is okay. Or
yeah, you can.
F of R
you may have some quintessence field or Chaplygin gas, but you have to put it together with the cosmological constant, not separate.
Yeah, together with the cosmological constant.
Yeah, why not? And then you have your right, you can do it. But it's not running, it's completely different. Physically, it's different thing, but it may be equivalent in the manifestations.
Okay. Can I ask one more? Yeah.
Sure.
Oh, yes, please ask.
I would like to your opinion on F of R modification late time. For example, those terms like 1 over R power n the Stravinsky introduced, are the IR non-local models, which are like Maggiore model or the Disser-Woodard model, which are good explanations logically for the cosmological for the dark energy problem.
Yeah, I can say about the action which Maggiore and his group used, because they worked with terms like R 1 over box square R, or R menu 1 over box square R menu. Actually, in this first paper by with Edik Gorbar when we, in this paper, which I cite by the of this transparency, we introduced these terms. Okay, and why we introduce these terms? Because we know that this story about form factors does not work for the cosmological constant. So the cosmological constant, you don't have form factor because any box acting on constant gives you 0.
Yeah.
And then we said that instead of cosmological constant, you may have R1 over box square R. No. Why it is very, very close to the cosmological constant? Because if you make a global scaling of the metric, okay, then this term scales exactly like a cosmological constant for global scaling.
Mm-hmm.
Okay, so the difference between this term and the cosmological constant term is only appears when your scaling is local. So it will be weak. So these terms are almost cosmological constant, but not exactly cosmological constant. So they give you like equation of state, which is not -1. It gives you equation of state, which is -1 plus some epsilon. And this epsilon is very nice to have because you may have your perturbations, you may have your cosmological data and compare with the data and so on and so forth. Now, this is nice. Now, what is bad part? First of all, I tried to obtain these terms, which were 1 over box square R, 1 over box square R, and I failed to obtain them in any possible way. So from spontaneous symmetry breaking in curved space, in quantum corrections, you never have these terms. This is not a problem, of course, because you define them. And the second problem is that, once again, you need cosmological constant, as I explained, okay? So you cannot have it without cosmological constant for these formulas and so on. So if you put R1 over box square R, it must be an addition to the cosmological constant. It cannot replace the cosmological constant.
Okay. By the way,
So as
earlier
an addition, it works very well, no problem.
Earlier you said quintessence, single quintessence cannot mimic the running of lambda. Is it possible f of r modification?
It can mimic until some level.
What about f of r? IR non-local models like Disser-Woodard model or f of r model? Any f of r?
The same thing. I mean, you can mimic something to some extent. I mean, to the perturbations. But if you take, let's say, with the available data of today, probably you can get the same results or not. I'm not expert in observational cosmology.
Okay.
But after that, at some point, of course, there will be some difference. But you can complicate your model with a function of R 1 over box R, like Deser and Woodard. You can make it more complicated, take more complicated function. The same with R 1 over box square R. Put one more term, 1 over box R. Put 2 such terms with arbitrary coefficients, and you have you can provide the coincidence with any finite number of data.
Okay, understand. Thank you, and thanks for
That's why you cannot, in principle, compare the two models which have different number of adjusting parameters. Statistically, if you have one model with 3 parameters and another model with 2 parameters, so they are not good to compare between themselves because one has one more degree of freedom.
Yeah, you're right. Well, unless we have more precise observations, then maybe it's possible to distinguish.
Yeah, in principle, yes. In principle, yes.
Okay, more questions, please. I guess everything is so clear that people don't want to ask more questions. Okay.
I should tell something else. To these same people I told several times he's here.
Okay, maybe this is a reason, because usually we have a little bit more questions, but okay. But I think that we can stop now. Thank you very much once again, Ilya, for your very clear presentation. Thank you very much. I hope to listen once again with tomorrow in Russian. Okay, yes.
Okay,
Thank you very much. Thank you.
Okay, thank you.
Thank you.
Thank you, Ilya.
Okay, thank you.
Thank you. Bye-bye.
Thank you very much.
Okay, see you.
See
Bye.
you.
Thank you, Ilya. Bye-bye.
Bye-bye.